Hey guys, welcome to Deep Dive Buddy. Today we solve lead code problem of the day, and this is the minimum cost to convert the string number 2. And previous day problem was minimum cost to convert string number 1. So in these videos I will explain, this will be the architectures. First of all I will explain the questions, then go to the example test case for the simulations part and discuss the near brute force approach and why it's failing, and now go to the deeper for the optimal solutions. And optimal solutions consist of three things. First one is it's use trie, dynamic programming, and fluid versus algorithm. And at last, after the discuss showing the code, I will analyze the complexity part, and I will discuss each part in details. So but it would be better if you go to my previous video and watch there, because there I already discussed the Floyd Orson's algorithms and the dynamic programming part. uh, yeah, so this will be the better for understanding, but I will explain here in details. Now let's go to the problem statement. So problem statement is almost similar to the that is we are to string and to do this there are few. So first of all our original, change and cost array. For this original I take the example of the code positions. If it is converted to age, it will take the cost of 3, and finally age the 4 target, and over here already given explained out this. So I think the questions is here. We are given boosting question I will repeat, and you have to find the most of conversions and the given original and change. We already, that was string number 1, and this is the case in the second problem. So due to this, it will be fastly built. This will tag as hardware. So next one is let's give and we can take subjects. So we are taking one DCD, and we can take something and convert it to these constants. And for something into something, follow the two rules. Follow one or two. Follow the rules one exactly same segments. That means let's say we are taking a substring that have I and j, and another substring. Let's say this one is substring number 1, and another substring is substring number 2, and these have the starting index k and ending index m. Similarly, for substring number 1, its starting index is I and ending index is j. Let's say these two are substring. Let's say you can say this is substring number 1 and this is substring number 2. Now to exactly same segment, what I mean is it's have to be like I equal to k. That means starting index of I for this substring and ending starting index of second substring have to be same, and jth index, like this is the last index of the first substring, should be same as last index of the second substring, that is j equal to m. That means we are taking same substring again and again. This is the segment. That means initially we take dct as first substring, and let's say it converted to efg, and again we are taking the efg as a substring and converted to another operations. That means we taking the same segment. Otherwise it should be disjoint. Disjoint means there are no overlapping. Let's say we are given as a b c d e f, then if we take this substring and if we take d e f, these are the two disjoint substrings because there is no overlap. So basically these two conditions is restricted, that we cannot take the partial overlap. That means if if the string is a b c d e f, let's say in first operations we take a b c d as a substring, and in the second operations we take the d as common and d e f. So here it is partially overlapped, this portion is partially overlapped positions. So these operations is not allowed. We are strictly bound to either disjoint or otherwise exactly same. I think these two conditions is clear. Now go to the test case simulations part. So as if you guys look into my previous video, I already show how to build the graph according to the given problem. Let's say there is only restrictions from the original element, we can build the changed element. So this is the directed graph, and there is also have the cost. That means this is the edge weight. You can consider this is an edge weight. So now according to these conditions, I build the directed weighted graph. So this is the BCD. From BCD to CD, it takes the cost of 1. This is the edge weight. Similarly for FGH to THH, it will take the cost of 3, and from the THH to GHH, it takes the cost of 5. This is the 5. And now the source string is given as ABCD. These two are source and target string already given. Now let's check the first positions. This is A and this is also A. These are two matching. Now let's move forward. So B, over here it's C. It's not matched. It is not matched. Now in either let's search in the conditions. Let's me minimize a bit. Yeah. So let's find the whether B is present in the whole graph. No, there is no B is, only B is present, that will convert it to C. No, this operations is not allowed. Let's increase these positions. We taking the BC as a substring. Now either BC is present in the graph. No, the BC is also not present in the graph. Now increase the BCD. Now is BCD is present? Yes, this is the BCD. So BCD, from BCD we can go to the CDE part. Whether we need CD in the targeted array? Yes, we need the CD in the targeted array. So we consider these operations and it will take the cost of 1. So cost equal to 1. Minimum cost you can say. Okay. So now this part is already processed. Now let's start from the second positions. Next positions. That will be the E. We have already processed this much and we start from E. Either E is same? Yes, E is same. Now go to the F next position, that is F, and over here G. Either F is present in the graph. No, single F is not present. So we increase the window. So F and G. We check for F and G. F and G also is not present in the graph. So we also again increase the FGH, like next element. FGH is present. Yes, FGH is also present in the graph. So from FGH, can we go GHH? This is the last element of the target, like segment. Can we go to the GHH part? Yes, we can go. How? First of all, FGH to THH by the cost of 3, and from the THH to GHH we can go cost of 5. So the total cost, it will be 3 plus 5, and this will be 9. This is the total cost, and also expected output is also 9, and we are good to go. Now let's come into the constraint part. You should look into, every time you should look into the constant before jumping into the solutions. I mean to say that before creating the solutions, if you look into the constant part, so there are source and targeted string given as, and it is quite low, that means 10 cube, and you can perform the let's say source length. Let's say SL equal to source dot length. So you can perform the SL square. This will give you the 10 cube square, and this will give you 10 to the power 6. This operation is acceptable. How I saying that? For 1 second we can do 10 to the power 8 operations. So any program under 1 second is acceptable normally in the LeetCode and also other platforms. Now go to the second thing is, this is the lowercase English letter. I come into this part later, and this is also important. This is also important informations. Now go coming into the cost dot length, original and the changed, all are same and also have the low constraint. So let's say you take OL as original dot length. If you consider this is the thing, so over here also function, let's say, and then you are allowed to perform big O of OL cube. Why? Because 10 square cube, it will give you the 10 to the power 6, and it is also acceptable. This is a important information according to the time complexity and the algorithm also, and cost over here given as 10 to the power 6. Now if you look into the, if you already watch my previous video, there I already discussed the uh, algorithms of Floyd-Warshall. So Floyd-Warshall's algorithms basically takes big O of n cube operations, and you are allowed to perform big O of n cube operations. Now next thing is define the nodes. As in the previous problem, there are only a single character in the original or change array. There are single character. That's why we take the array of 26, and this will give you like node number can go at max 26. This is the node number can go. But how we know that? How there are many string possibles in the original or the change array. So how to define this node number? So what we can do, to define the node number, we start a variable, let's say num of node. We can initialize by value 0, and each time we get the new string, we increase this node number and save in map, that you can say hash map. I will discuss later. And another thing is why you want to apply the Floyd-Warshall's algorithm. These algorithms basically compute the, let's say this is the dist of, I will explain upcoming slides detail, but I will just showing the glimpse of it. So it will give the distance, minimum distance between I and jth node. Okay, this is give the minimum distance, so we can compute easily. If you look into the last example that where I discussed, so to find this from FGH to GHH, we can pre-compute the minimum distance and it will give you the 8. But if we want to compute the CD to GHH, it will give the infinity, because there is no connections exist between CDE and GHH. Okay, so you can say the brute force approach simple. Like, first of all, we have to define the node number that I already discussed, that we can initialize by num node equal to 0, and each time we see the new string, we will increase that variable and save in the map. And each time we need that, if the string is given, so we just query to it in the map and we get the node number there. This way we can get the node number as the given in the constant, that it will be 100 at max, like original or changed. So there are original and changed, their node number can go at max to 100. So this is also smaller. Now, for why we want to apply the flow reversal, so that this will be the pre-compute part, pre-compute part, and we pre-compute all nodes to another nodes a minimum distance, and after that we have to recursively search for the optimal. How we recursively, what I mean to recursively, let's say their source node is source string is A B C D E F H, and yeah, let's say, yeah, G H. Okay, let's go back to the last previous example. So what we are doing over here is, yeah, we are checking, we are placing one like one iterator over here and one iterator over here. Let's say source string one iterator and target string one iterator. So if this two things is match over here, first index for the 0th index it is match, so we increase that iterator and go to the second positions, and here B and over here is C, it is not match. Let's erase first to get the better clarity. Okay, now, so we check where A is match with A. Yes, it's match. Now go to the second index B, and over here it's C. Now we have to find whether it is exist. If it is not, then we increase that thing, BC. But in some cases, let's say BC is also exist in the graph, but that is not the optimal. So we have to process each substring, each substring, and take only minimum. So let's say we already process to the index number. Let's say when we process this part B C D E, this will be like 0 1 2 3 4 5 6. So let's say we already processed up to node index number 3, and we are processing for index, we start process, start for index number equal to 4. We start for index number 4, and we process that things and save the answers. But if the index up to index number 3, let's say there are string already exist BCD directly to the ACDE, this thing with the cost of 1, so that would be the better options. So we can go for that, because what is the, okay, so over here also 1, let's convert it to, just for clarity, so it will give the cost of 2. But for up to, if we, now if we define hypothetical situations where, let's say BCD to ACDE, it's give the cost of 1. So if we apply these operations, it will give the minimum answers. But after these operations, these two processes done, we have to compute for index number 4. But for this fast iterations, we already computed for the index number 4, and we have to again compute for index number 4. So there it is comes the dynamic programming, we can store for the index number 4 operations, like minimum operations up for the index number 4, and we can simply return over here. Let's say in the dp of I we store the minimum operations needed. So if it is, we already computed dp of 4, if it is already computed, then why we again to compute the dp of 4? We just, instead of doing that, we just directly return to the handler that this is the answers which you are looking for. So here it's dynamic programming come. I will discuss also in the deeply. Now I think you understand it's a recursive problem. Also we can use dynamic programming for the optimizations part, and at last we just return the answer, whatever is the minimum answers we are already calculated. Now if you are doing this way, like if you are using the for the to the define the node number, if you are using the unordered map, so it will give you the time limit exceed. Why? Because it will compute. And also if you are thinking about doing this, let's write some brute force approach. Okay, so first of all, let me add a page. Okay, so you can say that let's for the get node number, you can use unordered map, but it will mostly fail because of because it will have more costly operations, that will be the TLE. And if you are thinking that let's say there is CDEF GH, this is the, let's say this is the source string, and in the target string is CDEEFG. Let's say this is the target string, and if you are you are thinking about that, you in the, let's say in the substring, let's say source substring, you iterate from first pointer over here and second pointer over here. So if you are thinking about storing source substring and target substring for compute, let's see, you take, when you computed this one, you inserted here, and when you computed target string, you inserted here, and you are only checking whether these two substring is convertible or not. It can be checked under big of one operations. But if you again take the BC AB and also over here AC, and this way it goes as much, so it cannot it cannot be like optimized approach. Why? We do not need, this is not optimal. We do not need to like why it's not optimal, I think you understand. The for, let's say, let's pointer over here first positions, and you compute a whole string as and storing and passing that into the function. Let's say you are starting from the second positions, you again you store whole, and for third positions again you store whole. So this will increase the memory, so like this will increase the space and the time complexity. So this will mostly give you the TLE, as I already faced that thing. So now come into the optimized part, that we have to use trie. So what is trie? I will discuss in the next page. So let's jump into the trie data structures. So it's almost advanced data structures, but you can understand properly. So you can think about this way, that there is a node, and for this node we store something. Let's say this is the 26 space array, 0 1 2, just take that thing, that will be like 26. And for in the 0th position, this is the all the initialized as null, or you can say null pointer. And let's say we are this is have the few advantages, that it will mostly optimized for search word, insert word. So and in almost so much faster. So you can use for that, let's say you insert into the, instead of using unordered map, you can replace to by the trie data structures for the insert and the search purpose. So what you can do, as we already given that we only deal with the lowercase English letter. So you can define lowercase English letter. You can define a 26 space array that will go to 0 to 25, and for the 0th positions it will be like equivalent to A, one position is equivalent to B, second position is equivalent to C and D, and so on. And at the last positions it will be equivalent to Z. And let's take an example. Let's say a word hello. We have to insert this word. So to do this, all are the first of all initialized as null pointer. Initially it is null pointer and all are null pointer. Now let's take this is age positions. So if it is we take the first word, first character, that is age, and we for this we just point a new node that will be also consist of 26 space array. So it will be 26 space array. This will be already converted to H. And now we go to the positions of E. So it will be like 0, 1, 2, 3, 4, 5, 6. So it will be like A, B, C, D, E. This is the E positions. From here we again take another node. This will also be 26 character, like 26 space array. And we already processed it. Now process for L. We already processed. Now process for L. So let's say this is an L positions, and we again create an array of 26. So it will take again array of 26. Now process this L. Let's say this is that positions. So this is also 26 array position, 26 space array. That would be another node. And finally there is O. Let's take this one is the O. Sorry, right over here. O. And another thing, in the each node we also take this one. Okay, so you can consider this is a node, and this is the second, third, fourth, fifth, and this one is the sixth. So in this node we also place a variable. Let's say you can think about this way, that what is the id purpose. Let's say this is the id initially -1, and all id is initially -1. This is a simple variable for each node, -1, and id also over here is -1, but id here is not -1. Why? Because we inserting this whole string as an converted to the id, as I already discussed how to get the id or the node number. So you can insert this. Let's say this is the first element, first string. You can say the id is 0. So in the next time when you search for hello, you can efficiently search that. Like, you start from first character, you go to the root node. This is the root node. So you go to the root node and search whether h have the not null character or not. It is not null pointer. Yes, h is not null pointer. Now go to the positions E. In the you get the access of this as it is not null. So you go get the next node and find the E is not null positions or not. So it is E also is not null. You again go to the next positions, that will be the L. Over here L is also present, and again you go to the next L. So over here also L is present, and again at the last you go to the O, and you find O positions is also null. So you got this like you enter these positions, like you enter this node, and you check whether its id is -1 or not. If it is -1, then hello is not exist. If it is not -1, it hello is exist. So how you can check that? Let's say hel, whether it's exactly present or not. So you go first h, yes, h is present. Then you go e, yes, also e is also present. And you go to the L positions, L is also present. After L positions, you access this node. like this node is accessible from after the lth positions. But if then you check whether id is -1 or not. If it is -1, then hello is not present, and actually hel not, sorry, hel is not present. Actually present is hello, so you can search accordingly. But if you want to try to search for the prefix search is also possible. According to your logic, you can modify that things, and search, insert, delete. These are the few operations are very efficient for the trie data structures. Now you can think about this way, that let's define the node. What is node for this trie? It will be like, you can, this way you can define. This will be, let's say, node star, and let's say list. And when you initialize constructor via the constructor, so you can initialize list dot resize. I will explain the 26 and null pointer. Let's say pointer. I will discuss this coding in detail in upcoming slides, like in the editor also. So this way detail, and also you get the id, which you can say -1, and these two things will ensure. And also you have to define the trie logic, that will be for searching, for inserting. But how we apply this inserting to, like, what we are doing over here. Let's again come into the example. Source have, let's say, a b c d e f g h, and target have something like, let's say, c d e e g h h. Okay, so you are in the recursion part. So you will start from over here and over here. So instead of storing in string, you place a pointer. Let's say pointer for, let's p1 for root node, or root node 1, and p2, this is also root node of trie data structure. This is not one, both are the same root node, because we are using only one trie. So p1 is the root, pointing to the root node, and p2 also pointing to the root node, and it will search. If it is same, then we can skip it simply to the this second 0th index, one index. So it will be like b and c, and now you are pointing to the root node, and try to traverse in the root node. So you can do, for if it is present for the root p1, that will be the root node access. Is it present b element? If it is not present, so we can simply break and start from the next iterations, and we again start for the p2 also. If it is p2 root node, c is not present, then also we can break. Otherwise we can go to the we can traverse in the trie and go accordingly. So in any situation, p1 id, if you get that id, and p2 id, these are not null, and so you can convert it to p1 to p2 with via some cost. So you can consider that is a valid substring. So this will reduce the this will reduce the complexity part for the valid substring. I think how to use the trie is clear, and I will also explain the coding in the details, how we are actually using, and each part in detail way. Now come into the Floyd-Warshall's algorithm. Now Floyd-Warshall's algorithm, as already discussed, we are taking a distance array that will take, this will be the 2D array, and you can say distance of ij, and it will simply store the minimum distance between minimum distance uh, minimum distance from I to j. Okay, so to get this distance as a pre-computed way, we have to iterate. There is a simple idea. We are first of all we are simply initialize all the distance, initially distance of self node, that you can say distance of I equal to 0 for all I 0 to max number of nodes. This will be the initializations part. After this part is done, we simply I to j, let's say I equal to 0 to max node, I and from j also goes from 0 to max node, and distance of ij equal to minimum of distance of ij comma a cost of that positions, let's say cost of I. So this will be this will update the edge weight. So initially all the distance, all dist of ij is equal to infinity. So over here it will update if distance of I, that is no self loop, is also exist with the edge weight. So that will be the cost of 0. And another one is initializing part of this one, that it will simply update the edge weight of the initial iterations. Now start the iterations. That means we try to compute I to node j via the node k. That means let's say I and j is not directly connected, so initially this distance of ij gives the infinity. That means it is not connected directly. So if we compute the distance via k, and let's say this one is edge weight is w1 and this k to j edge weight is w2, so you get the answers in next iterations as ij equal to distance of ik plus distance of kj from k to j. So it will give you the w1 plus w2. But we have to like these steps. So it will be like so you can say the distance of ij, it will be updated something like this way, equal to minimum of distance distance of ij comma distance of I to k, and plus this will be like plus distance of k to j. This is the actual steps, and it will run over and over up to how many times? It will run 0 to max node number of times. Let's say k equal to 0 to max node number of times, and in each time I is also go 0 to max node number of times, and j also goes 0 to max node number of times, and we update this statement. And what it does at the kth iterations, this is the k, at the kth iterations we utilize k minus 1 nodes to compute let's say it will be like to compute distance between I and j. So yeah, distance, let's erase it properly, let's write it properly. So it will like compute distance between I to j. So this is the main thing. So if we run this k as max node number of times, so we can use all the nodes to compute each distance. Also, this will give you the optimal approach, and I think it is in the coding purpose. It will also be clear how to write the code for it, as I already discussed the overview of this problem. Now I already discussed this part, like how to from recursion to DP. Like let's again take the examples of that one: A, B, C, D, E, F, G, and H, and target string is this one: A, C, D, and double E, F, G, H, H. Let's see this one. Is that thing correct? I think it is have the extra. Okay, let's erase it. I think from E, so E, G, H, H. I think it's now correct. This is, yeah, this is now same number of characters as the source and target also. Now for the recursion part, like first of all we are taking this one and check whether it is same or it is exist in the graph. So if it is convertible, then we can take it is as convertible. Now we process for this whole string as a sub problem. But if it is, and another case is we take AB as a string and consider another part. So you can say AC over here and consider another sub problem. So this will be recursively solvable, and there is also occurs similar situations, like we already process up to this part, and this approach is possible to solve via, let's say, two way. First of all, one way can be we take AA as same, so we ignore it, and we convert BCD to CDE via some cost. Let's say this is 5. And another case can be this way, that we take AB as a whole string and CD also a whole string, and we convert AB to AC and CD to DE. Let's say this is AC and with the cost of 1, and CD to DE with the cost of also 1. So it will give you the total cost of 2. But that is not the main thing to consider. Is we have to process EFGH 2 times. But why we want to process that thing? We can save the answers for the EFGH part, and in the next iterations, let's say we process this one, then we process this one. So in the first iterations we just save the answers for the EFGH, and the second iterations we just return that from that stored answers, because that will be the minimum. So in each steps, uh, like, okay, so each steps we calculate minimum cost. We calculate the minimum cost with and save it in places, and save also, like, and save it, so that we can refer in the next time. So this come in the dynamic approach. So simple over here, let's say you take an DP of I. What it mean? So it will store I to end minimum. What is what is minimum cost? What it mean? So when we try to compute DP of I, so it will compute as minimum of DP of I, and to convert that single characters from ith positions plus DP of I plus 1, because we already calculated the DP of from the DP of I positions to end. So if we able to convert that single character right now, then we can update the answers of for the DP of I. This how it will simple store. And now jump into the coding part. let's this one, go to the first one. This is the starting point of it. We are given a function. This will be the long minimum cost. We have to write the functions. Let's start from over here. Now this is the LL of number of nodes. So it will simply store, it will simply track, let's say track the number of nodes. It will track the number of nodes as I already discussed. Okay, let's explain over here. So let's add a page for that. Okay, this is the number of nodes. That means we just calculate, it will initialized as 0. You can see these things over here, and it is initialized 0, and each time it will insert a new string, it will increase and consider that as an like node value. And also we are taking a try as a variable. I will explain the try implementations also. First let's focus into main coding part. And now this is the get id functions. So as I already discussed, it will take string as an input, and if it is not present in that string, so node number is a unordered map. You can say this is the unordered map node number that will take the string as a key, and value for the long that will save the node number. And if it is not present in, that means count, it will be the false. If it is not present, this will give the false, and as not sign is already present, so for not false it will be give the true. So it will insert that node number and increase also the number, and return what is the actual value of the node number. So it will give you the id of that node according to the string value. Now we insert the each string in the trie data structures, also the map the IDs. So it will take, first of all we traverse through the original array size, and original and the changed array both are the same. So we just get the original array size and traverse it. So first of all u is the original array elements, and we get the id. So u is the id of the original array element at the ith positions, and v is the id of changed array of the ith positions. Now both are inserted to the try. So this will inserted try with the id of u, and changed with the id of v. So these two are inserted in the try. I will discuss how this insert functions is already written over there in later. So now you track the maximum number of nodes. This is the num node. As num node is increases, as the number of node increases, so that will be the maximum node what is at the end. Let's say you have two string, let's say SA and SB. These are the two string, and as the node value, so initially it will be 0, and when you get the SA, so it node value is 1, and when you get the SB, it will go to the node value of 2. And if you look into the last, after all inserted, so the number of nodes equal to 2, that would be the node value. Now so that is why we take the maximum number of nodes. Now as I already discussed the distance array, so it will be 2D array. That maximum, it will be 2D array of maximum number of nodes, and this is also maximum number of nodes, and initialized via infinity, initialized through the infinity. Now it initialized for the distance. There is no self loop exist, like weighted self loop. So distance of I equal to 0. That means from the nodes, let's say this is the 1, we go to the 1 with the 0 cost. This means distance of I equal to distance of I equal to 0. Now come into the second part. So we again traverse the original array size, and we again get the node id. Over here also get the node id, and we update the distance of UV with the minimum of distance of UV and cost of I. What it mean? If the from node U to V, if there is edge already exist with the some cost, let's say cos C1, so we just update distance of UV. This is the node ID with the cost of 1, because initially all the node distance is initialized as infinity, so it will be updated in these steps. Now apply the Floyd versus algorithms. So it will traverse, like it will iterate max node number of times, and in each iterations we traverse the from I0 to max nodes, as I already discussed over here. And it will be like for the J also 0 to max node number of times. And you can place like conditions over here, so that you can efficiently calculate without entering into the loop. So when you are iterating through this I, before entering into the jth loop, if the distance of ik is infinity, that means it is not a valid answer. That means the node we try to calculate from I to j distance via node k. But what it means, distance of ik equal to infinity, that means there is no connections, so we do not need to consider these k nodes to the I node to calculate the j node. So this is the waste of time. If we calculate that thing, it will be waste of time. And similarly for the j, when we are iterating through the j, there is distance of kj equal to infinity, then we can continue. What it means, we want to calculate similarly like I to j via k node, but the age of k to j is also does not exist, so we do not need to consider that as an answer. Like we can go to the loop, but it will take the time complexity, so it will be it does not give any constructive computations. If both of these links exist, then we can compute the minimum of those two things via k nodes, so it will give the minimum distance between any two nodes. And at last we have to calculate the DP. So dynamic programming calculations, let's initialize n as source dot size, and also resize to the n plus 1, that will it can go as the DP of I. It will I is track the source index, it will track source string index, so it can go at max, so initialize via n plus 1, where n equal to source string size, so that is placed over here. Now another important thing is dp of n equal to 0, that means cost to convert empty suffix equal to 0. That means we already convert, this is the string is given as s, and we are over here, so this is the empty string. It does not need to compute any it does not need a cost to convert empty string, so it will be the cost of 0. That's why dp of n, that means for these positions to convert the string, it will give the cost of 0. Now start, this will be the start index, start from last and go to the 0th positions. For each start index we have two options. There are options A, if the character matches we can skip them with the 0 cost. That means, as I already discussed, let's say there is A and source string is A and target string is A, age B. So these are the matching with this one, so we can skip with the cost of 0. We can do that. Otherwise, option B, try to find the substring in the try. Otherwise we can, let's say we can skip these things, but there is position at the last position C, and there is D, and but there are graph is only for ABC to ABD. This conversion is allowed, but no C to D conversions is allowed. So if we skip with the BC completely, then we cannot find the answers for the CD and we return the -1, but this is not the case. We have to take the whole string ABC for over here ABD, then we can compute the answers as 1. So this also the case where we can do, we have the option B. For this case we have option B. Try to find that substring in the trie. If it is present in the trie, that means we are in the good positions for the node value. And let's say for the first options, that means the character already matches, so we can simply update as start index and start plus 1 index as start plus 1 index value plus 0 equal to dp of start index. So we just update that thing. And second option is a tricky one, these options. So as I already discussed, we take 2 pointers, that is node star of pointer 1 for the trie root and node star of pointer 2 for the trie root p2, the p1 and p2. So again we start from the start index to the last index and I plus plus. Now traversing the trie. So for the p1 we try to get this for the source word, and for the p2 we like traversing the target element. So what it mean? P1 is present of source I. So if it is present, then it will give you the true, and it will give, for not true, it will give you the false, and if it will break the loop. No, sorry, it will leave the loop because it is already false. So it will increase the, it will go to that pointer. That means if it is present, then it will go to the next, this line executed, and if it is not present, that means these portions is give you false, and not false give you the true, and it will break the conditions. That means this is not a valid substring. And similarly for the target, no target, like we traverse for the target in trie. Now for p2 is present of target I. If it is not present, then this will give you the false, and not false give you the true, and it will break the loop. If it is both the things is present, like p1 pointer have the present, then it will go to the next pointer, and p2 also next pointer, and at any particular positions, if both the substring is valid, that means p1 id not equal to -1 and p2 id not equal to -1, then we can compute this is a valid substring conversion. So we can update the like dp. We calculate this one, let's say distance of p1 id, p2 id not equal to infinity, that means it is possible conversions, and dp of I plus 1 not equal to infinity, that means after like substring is also not equal to infinity, like substring is also convertible, then we can compute that distance, as I already computed the distance array, and plus dp of I plus 1. This is the cost for conversions source to target, and this is for I plus 1 cost. So we updated for the dp of start index, and as the dp of start index updated in each iterations, at the last iterations we just check whether dp of 0 is also updated or not. If it is not updated, that means it is already infinity, so in that case we have to return -1, that means it is not convertible in any situations. Otherwise we can return to the dp0, that means at the 0th positions the minimum answers will be stored, so it will be give the minimum cost to answers. I think its core part is clear. Now jump into the trie data structure part. So as I already discussed, trie will take the 26 space character, like 26 space array. So you can say vector node star list. This is a struct, and it also have the id which is -1, as I already discussed in the like dry run part. So this is a constructor, so it will just resize that list to the 26, and there are few functions, that is get node. It will simply return the uh, pointer of that node star get node. It will give the take as character ch, because all are the English alphabet lowercase letter. So it will give you the list of ch minus a, because ch is a character, and minus a it will give you the that index. That means for a it have 0 index, b c d it have b for 1, c 2, d 3, and so on up to Z, this will give you the, I think, yeah, then that will be the according. Okay, so now let's this is the another function that will set the node. It will take the which character to set and what the node to set, that is the pointer. So it will just simply assign that node. Another one is I discuss so many frequently, that is present or not. So it will be like, it will take the that character and it will check whether it is null pointer or not. If it is present, that it is not the null pointer, so it will give you the true part. Otherwise, if it is the null pointer, then it will give you the false. So this is the node, and each to make the try, there are so many nodes. So we are taking a node star root. This is the root node. In the try initialization, this is the constructor of the try class. So it will be like create a new node for the root. A root is the pointer, and it will in the pointer we assign a node, new node. Now insert functions. Insert function take two parameters. That will, first one is string, what to insert, and what is the ID. Now we start from the root node. As I already discussed how it actually work. So we go to the each character in the S, that is the string is passing over here as an argument, and if it is not is present, that means if it is not present, then we set that positions as new node, assign as a new node, and go to that positions. And if it is already present, we directly go to that node. And at last, when we in the last node, we just update that ID so that we can find that it is a completed string. And this is the try data structure part. Now there are few variables over here, that unordered map is for the node number, to track the node number. Maximum node is for the total number of nodes. Distance is 2D array, as I already discussed. And taking const long as infinity as it e1 e18, it's mean 10 to the power 18. And taking also dynamic dp vector, and try as a try pointer, try class pointer, so that we can in here we initialize it. So yeah, I think it's discussed for the coding part. Now let's jump into the that part, like complexity. So what is the complexity part? Let's jump into that. Okay, let's reduce the size of here. Okay, so for complexity, okay, let's, yeah, so the complexity part over here, let's take spaces for over here. Yeah, so time complexity, it will be like first of all, there are no time complexity for these parts, or you can say node count, it will also give you in big of one time. And from the next steps over here, so it will take big O of original dot size. This will take the, and try inside is so fast, and you can say it will try inside will take the word dot size, whatever word dot size, and also change word dot size. So you can say that original size cross each element, like word dot size, this will take. And after that, this will take maximum nodes, so it will be like max node, or again original big O of this portion, it will be like big O of original dot size. Let's take OS as original size. After that, Floyd Warshall's algorithm, it will be like big O of, okay, it will take big O of max node, max node cube. And another thing is dp. So dp will go as max as 0 to n minus 1. It will take n. Also over here 0 to n starting is n. You can say n square as an answer, and where n is the source dot size, so you can say source size square, because source size square. Anything else? Yeah, these are the complexity. Okay, so you can say this is the time complexity part, and it is acceptable under the conditions, as constraint is too low for the space. You cannot get the space exact space for the try, because it will take the less space, but you cannot give exactly how much space it will take. But instead of apart from that, max node number will take at max, like node number will take 200 space at max, because 200 maximum node is possible. Also distance we're gonna take distance, how much it will take, let's check it. Distance will take maximum number of nodes. This is also 200 cos 200. And anything else? Yeah, dp also take n plus 1, where n is the source dot size. So let's say ss, big of ss. Yeah, these are the space complexity of it. Thank you guys, thank you for watching. Stay tuned for more videos. I will upload the notes in the descriptions, and also link the coding, this coding in the descriptions also. Thank you guys.